So, good evening, everyone. So, I want to continue from where we stopped in our last class. That is subsequences of sequence. In our last class, we have defined the subsequence of a sequence as a function xnk, okay, where n, okay, is a codomain of another sequence nk, and this maps to R. Okay, we have said that this happen. Okay, we call this a subsequence. Okay, and the formulation is from this mapping. If you have two sequences, xn, where the domain is natural number and codomain is R, and we also have another sequence nk, where both the domain and the codomain are natural numbers. Okay, so this, the codomain nn, okay, if it moves to this place, okay, so this means that the subscript here can be replaced by nk. Okay, so that is, if you are making the domain of the xn to be the codomain of this sequence, okay, what we have will be what we have from these two will be this, okay, and this is called subsequence of the sequence xn. So having said that, we have considered some examples of a subsequence of a sequence. For example, if we are given xn to be the sequence this, okay, where this sequence is 1 over 2, 1 over 3, and so on and so forth. Okay, we can derive subsequence of this as follows. Okay, you can say xn1 is similar to 1 over, okay, the function there is the vector n. Okay, so if you make k here to be 1, okay, this becomes xn1. Okay, and it means we should replace whatever was here, we should replace it with n1. Okay, and if that happens, furthermore, you can select some sequence of nk. Okay, because this one satisfies the condition that n1 is less than n2, okay, less than n3. Okay, so for the sake of this, if we make n1 to be n plus 1, for example, okay, we can make n2 to be n plus 2, can make n3 to be n plus 3, and this goes, okay, that is, whenever we see n1, we replace it with n plus 1. Okay, so, and this is this. Okay, so listing some of the elements of this sequence, we have that this is 1 over 2, 1 over 3, 1 over 4, and so on and so forth. Okay, and we will see that the only element that is missing here is just 1. Okay, for this reason, the sequence xn1 here, okay, is a subsequence. Okay, or we can say it's a subset using the notion of subset of xn. Okay, again, we can derive another subsequence by replacing this end will be n plus 2, okay, and so on and so forth. Okay. So where we are going now is that whatever happens to the sequence of real numbers, okay, it must happen to its subsequences. For example, what we observe in the sequence is that as n goes to infinity, this sequence goes to 0 as n goes to infinity. Okay, as you can see, the sequence here is decreasing to 0. Okay, and also if so this is going to 0, all of its subsequents will also behave the same way. Okay, similarly, if n goes to infinity here, okay, you see that this also goes to 0. Okay, and this happens to all the subsequences of this sequence xn equal to 1 over n. Okay, so for this reason, we can now make a law in form of a theorem, okay, that we stand as a law for what we have just said. Okay, so let's get the theorem. Theorem. So theorem says let xn be a sequence of real number okay. So if xn converges to a limit if xn converges to a limit L, then all its subsequences, or we can say all of it, all of its subsequences converge to N. Okay, so these are a simple illustration of what we have earlier. Okay, so if you have a sequence which converges to a particular limit, or which converges to a particular limit, all of its limits okay also converge to that limit. Okay, so and the proof of this is not far-fetched. Let us quickly see that proof. Okay, from the statement here, it is suppose that the sequence xn converges to L. Then by definition, that is by definition of convergence, okay, that will be given epsilon greater than 0, okay, epsilon that we use to measure the accuracy of the sequence, okay, given epsilon greater than 0, there exists n of epsilon such that the difference of xn and its limit is less than epsilon for n greater than n of epsilon. Okay, I think we are familiar with this law. Okay, so since we have this, you will recall that if you have a sequence, okay, to form its subsequences, what we do is to replace the subscript here by nk. Okay, so what we just do is to introduce the nk, which is the subscript for the subsequence of xn. Okay, and how do we do that? We select k belongs to n such that nk is more than n of itself. And what we are trying to do here is this. Okay, this k is an integer from the natural number. Okay, and what we are trying to do is to replace this n with nk. Okay, so with this, what we have done is we have replaced n with nk. Okay, so and for this reason, this formula becomes xn xnk minus l is less than epsilon. Okay, and by definition, okay, you can conclude that therefore snk converges to l. Okay, so the proof is straightforward as we have it here. Okay, we first assume that the sequence converges to a limit n, and then we consider its subsequences, which is the xnk, and we place n with nk, and by that, okay, the proof follows. Right. So that is that on the theorem. So, and the summary of it is that whenever we have a sequence, if the sequence converges to a particular limit, all of its subsequences, okay, will also do the same. On the other hand, if the sequence is divergent, similarly, all of its subsequences too will also be divergent. Okay, and we can see this from the sequence of the real number. Or a sequence of so let us give it as a mark. So let xn be the sequence of 1, 2, 3, 4, 5. Okay, and we can think of subsequence of this as xn1. Let this be let's say 2, 4, 6. That is, we are picking the even numbers among it. Okay, and this will be 8. Okay, another subsequence of this will be the odd numbers. Okay, you can pick a subsequence that is a multiple of 3. That is xn3. A multiple of 3 is also a subsequence. Okay. Okay, these are all subsequences of this. Okay. So now, the first sequence we have is a divergent sequence. Okay. All of the subsequences that we will formulate from here will also be divergent. Okay. As you can see, 2, 4, 6, 8. Okay, it's going to infinity. 1, 3, 5, 7 is also going to infinity, and as such, this one is also going to infinity. Okay, so this is a kind of a kind of converse of that earlier theorem. Okay, so that is that. We now move on to a theorem called the sandwich theorem. Sandwich theorem. So we'll first of all give these are a case where we have many sequences, and this sequence obey the law of the subsequences. And if that happens, if you have some information about the particular sequence, okay, you can conclude as we are about to do now. Okay, so the sandwich theorem. Okay, so the theorem goes thus: let xn, yn, and zn be three sequences of numbers okay, and these three sequences are related as follows, such that xn is less or equal to yn, and yn is also less or equal to zn. Okay, so this happens for each n in n. Okay, what you are saying is that if you are given three sequences and the three sequences are related by this order, I think xn is like a subsequence of y, and y is like a subsequence of zn. If there are information about this sequence and this, do not have any information about this. Okay, what I'm about to say that if anything happens to this, okay, or if the sequence xn now zn converges without any information on the middle sequence, okay, so the middle sequence by this relation will also be convergent. Okay, and let's see this fully. So assume that sequence xn converges to n, and zn also converges to n as n goes to infinity. Okay, then because of this relation, then we can see that yn also converges to n as n goes to infinity. Okay, so this is what the sandwich theorem is doing. We have information about the outer sequences. Okay, so based on that, we are now based on what we know about this, we are now judging this. That is what the theorem is saying. Okay, and you see that the sequence yn here is sandwich between xn and yn. Okay, so let's quickly see the proof of this. After which we'll give a remark or a consequence of this theorem. Okay, underneath for this theorem is what referred to as the skews theorem. Skews theorem. Okay, skews theorem. So let's see the proof of this. Okay, from what we have here, there are three sequences and they are related by this. Okay, all the information we also have at hand is that the two outer sequences are convergent and their limit is LL. Okay, I would say if you have that, okay, based on the judgment on these two, we can say yn being the sandwich of the sequence, okay, it's also convergent. So we now say that suppose that xn, yn, and zn are sequences with xn less or equal to yn less or equal to. So by what you have here, by the function we have here, we now say since both xn and zn converges or converge to n. So by definition, so we can have this for given epsilon greater than 0. There is this n1 of epsilon, and the n1 of epsilon is standing for xn, and the n2 of epsilon is standing for the zn. Okay, that is the last n for both xn and zn. Okay, are n1 and n2. Okay, such that xn minus z is less than epsilon for n greater than n1 of epsilon, and zn minus z is less than epsilon for n greater than n2 of epsilon. Okay, so these happen respectively. So I think we are all following. So now let's n of epsilon be equal to the maximum of n1 of epsilon and n2 of epsilon. Then for any real number n, the following rules. So we are coming from here. We are bringing this solution down here, and what we are trying to do here is that so what we are trying to do is to see that if you have xn to be less or equal to yn and yn is less or equal to zn. Okay, so if we remove a number here from the other structure, the law of other structure, so this implies that xn minus zn, okay, is less or equal to yn minus z, and this is less or equal to zn minus z. Okay, and we have this because of from the other structure. Okay, I think that is a property 3 under the other structure, O3. Okay, if you have a relation that are associated by a particular order. Okay, if we add an element to the left-hand side inequality, and then we add the same element to the right-hand side of the inequality, the order will preserve under the last structure. Okay, so let's move this off. So since xn and zn are convergent, then for epsilon greater than 0, we get from this relation, and since we know that this is convergent, this relation will use minus epsilon will be strictly less than xn minus n less or equal to yn minus n, and this is less or equal to zn minus n. And because this zn is also convergent, this also will want less than a positive epsilon. Okay, so we know this because of the convergence of the two sequences there. Okay, so by transitivity, we have what transitivity is really is that since this is less than this and less than this, okay, you can partition this and say this is minus epsilon, okay, less than y minus z. But can also partition this and say this is strictly less than this. Okay, so this implies from the definition of absolute value, or from the properties of absolute value. Okay, this implies that yn minus z is less than epsilon. Okay, from the properties of absolute value, that is the property we earlier discussed, that if there are two real numbers, a and b, okay, and this condition is satisfied. So if this condition is satisfied under the properties of absolute value, this means that this is minus b less than a less than b. Okay. Okay. So this relation is true. Okay. This relation is true. Okay. And that's what we use it exactly. And this goes for n greater than n of epsilon. Okay. So hence, you will see that this relation means that the sequence n is convergent. So that relation means that the sequence n is convergent. So therefore, yn converges to n. Okay, and that is the end of the proof. More so, we can also bring out the consequence of this. Okay, or let us first of all examine this by with the aid of an example. Okay, an example of something of this nature. So if you are here with me, you can bring out your calculator. Okay, because we want to examine something using this relation. I want to check whether this is satisfied or not. Okay, so bring out your calculator and you do as I instruct. So example of this. So let xn equal to the sequence minus 1 over n start from 1 to infinity. Yn be equal to the sequence sine n. Okay, sine in trigonometric form, sine n start from 1 to infinity, and Zn is equal to 1 by n. Okay, so that this sequence are related. Okay, are related as follows. What we want to say is that this sequence, okay, follow this order, and if you follow this order, this means that minus 1 by n is less or equal to sine n, and the sine a is also less than or equal to minus 1. Okay, so for each n, in n. So as confirmation now, are you with your calculator? So what is your answer? So, for example, if n equals to 1, we'll see that this sequence here will be minus 1. Okay? And this will be less than sine 1. Okay? If you have your calculator, convert your calculator to radian. Okay? If you press sine 1, you see that minus 1 will be less than sine 1. And also, this sine 1 will be less than, when you substitute 1 here, this will be 1 over 1. Okay? You can check that on your calculator that this is true. Anybody there? No response, anybody there? Okay, so also if n equal to 2, okay, this will be minus 1 over 2, this will be less than sine 2, and this will be less than 1 over 2. Okay, sine 2 there will give us, let me see who is responding there. Okay, sine 2 will be this. Okay, so what we will observe is this. As n goes to infinity, can anyone respond to us there, please? Or I think it should be either sine 1 over n or so. So someone should respond so that we can, or let me do this myself. So we want to confirm that the equality is satisfied so that even if we don't know any information about the convergence of this, but we know about the convergence of this too. Okay, can use that to see that the sequence also converges. Okay, so let us simply confirm that here. Okay, I think it should be 1 by n. Okay, so if we confirm this, we'll see that this is satisfied. Okay, because we do not have information about the convergence of this, so as n goes to infinity, as n approaches infinity, okay, the last term is 0, okay, and this will be 0, this will also be 0, okay, so that is what we are saying. Okay, suppose we do not have any information about this, and this is communicated as a 1 by n. Okay, now what we are seeing here is this: if since 1 by n and this goes to 0 as n goes to infinity, then without any information about the middle part, we can say that sine 1 by n also goes to 0 as n goes to infinity. And this is so because this sine 1 by n is a sandwich sequence between the sequence xn and yn zn. Okay, so that's one of the uses of the sequence. There are many examples of sequence that satisfy this. Okay, we are only giving us, I think, one to do that. Okay, so let's see the consequence of that of the sandwich theorem. So we put that vocabulary. It says n and yn are sequences such that xn is less or equal to y for each n in n. Okay, if this happens for each n in n, so this is okay. Let's refer this to this. So this one says if yn converges, to L, then xn also converges, then xn as well. Okay, and the proof is similar to the theorem we have earlier. Okay, because in the last sandwich theorem, we have said that if we have three sequences that follow a particular order, this order, okay, whatever happens to this, okay, so the proof of this, okay, this follows, okay, from the sandwich theorem. Okay, so that is the sandwich theorem. We now move on to another fantastic theorem that is known as the Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem. Okay. Okay. We just have two more theorems to talk about before we draw the curtain for sequence of real numbers. Okay. So let's quickly see this. Okay. And this theorem will be proved by the notion of the sandwich theorem. Okay. But before the proof, let us sit and then give some examples or an example of a sequence that satisfies the Bolzano-Weierstrass theorem. Okay. So what this theorem is saying is this. It says if we have a sequence that is bounded, okay, but we don't have any information about the convergence of the sequence. Okay? So, but we know that this sequence is bounded. If we split the subsequences, this sequence into subsequences, okay? So, the theorem says every bounded sequence, okay, in brackets, converges or not. Okay, if a sequence is bounded, whether the sequence converges or not, okay, as subsequences which are convergent. Okay, so that is one of the things we want to get from it. Okay, so let's see an example of this. For example, the sequence xn equal to this. We have been given this sequence before that. The information we have about this sequence is that it is convergent. Okay? Sorry. The information we have about the sequence is that it is a bounded sequence. Okay? But it is not convergent. Okay? But if you are able to deduce some of the subsequences, okay, what this theorem is saying is that those subsequences will be convergent. Okay? So, and what we are able to get from there is this. Let's list out some of the elements of this. Okay, two things are possible. Okay, you can obtain the subsequence that satisfy if you replace this n1 to be 2, if you replace this n1 to be 2, okay, you see that what we will be getting here will be 1, 1, 1, and 1. Okay, we'll get a constant sequence, okay, which by our previous assumption is the combined sequence. And can similarly pick xn2 to be a sequence. If you replace this n2 to be 3, okay, you recall n1 is 2. If n1 is 2, replace 2 to what is there. What will be getting is 1, 1, 1. Again, if you replace n2 to be 3, that means the power of this term here is now 3. Okay, what will happen is that whatever we get here will be minus 1, minus 1, minus 1. Okay, what we are saying is that this sequence is bounded but not convergent. But we are able to reduce two of its subsequences that are both convergent. Okay, you will recall here that we have said a constant sequence is a convergent sequence. Okay, this is convergent, this is convergent. Okay, and where they are coming from, okay, that is the larger sequence is not convergent. Okay. Okay, so this is what the Bolzano-Weierstrass is coming to address. Okay, so having said this, I actually have said this is a theorem. Okay, that it is a law in mathematics, so that needs to be proof. Okay, so I'll give you the kind of a skeletal proof of this. Okay, so and I think I will send the material to you where you can see a web post proof after which we discuss the theorem of necessary interval. Okay, so let's describe how the proof of this will go. Just a description. Okay, so it's clear that proof. So you see, since xn is bounded, say above, say below by a naught and above by b naught. Okay, as we have it here. Okay, we have a sequence which is bounded below by a naught and above by b naught. So that sequence is anything between this interval. Okay. Now, in order to deduce subsequence of this bounded sequence, okay, it's variable by a naught and below by a naught. Subsequence of this will be some of the subintervals of this sequence. Okay. So if we partition this interval into 2 and let the middle point to be m naught, okay, the middle point is used in such a way that the interval between a naught to m naught is the same with m naught to b naught. Okay, and this m naught is nothing but the formula m naught equal to b naught minus a naught divided by 2. Okay, that's the middle point here. Also, you can choose either way. You can decide to choose this place or you can decide. So if you are choosing this, we see that from m naught to b naught is now a new interval. Okay, so it's a new interval. So we'll call this place a new point M1, and we'll call this place B1. Also, if we divide this interval into two, we have a middle point called M1. Okay, also M1 in this case is also B1 minus A1 divided by 2. Okay, so again, we now have a new point here. I'll call this place A2, we'll call this place B2, and divide this also into 2 to have M2. M2 is the middle point between A2 and A2, so that M2 will be equal to B2 minus A2 divided by 2. Okay? So, can continue to do this up to infinity, and what we will observe here is this. What you observe is this. You will observe that B1 minus A1 is similar to what we have here. This B1 minus A1 is similar to, okay, you see, it's like a term that is dividing from A to A. Okay? That means you can further express this as 1 over 2 into B naught minus A naught over 2. And as such, this will be B naught minus. So you recall see that this M2 also defines a term in form of B1, and B1 also defines a term with B naught. Okay? And of course, this will be B naught. Okay, using this inside here, this will be B naught, A naught over 2 raised to the power of 3, or you call it 8. This is 8. So as n goes to infinity, if you are missing at the middle point here, okay, what we have will be bk minus ak all over 2 raised to the power of k. Okay, so we can now refer to each of these as snk. Okay, each of these is now snk in such a way that this will be in between. This will be in between the sequence AK, let's say equal to SNK. Okay, so that if K is 1, SN1 is in between, okay, it is subsequences. Okay, for example, if K is 1, okay, this XN1 will be subsequent between this interval. If it is 2, it is a subsequent between this interval. If it is 3, it is a sequence between this. Okay, that's how we have that. Okay, so as K goes to infinity, okay, what will happen is that the we see as K, as we continue with the partitioning, okay, both A naught and B naught, okay, becoming A1, B1, A2, B2, okay, we meet at one point. Okay, similarly, we meet from here. Okay, we partition this again to meet this, partition this again to this. Okay, this is what we're getting. Okay, both of them will meet at one point. What we are saying is that this AK, okay, and AK will be the same. And both of them meet, it means they are skills together, okay, to meet at the point of to meet at the particular point and be here. Okay, so what you are doing is that if this AK, okay, meets at L, and BK as it is coming is also meet at L, okay, then SNK also goes to L. That is what the Bolzano-Weierstrass theorem is same. And we are bringing out the notion from the sandwich theorem. Right? So this is how we improve this. Send the notes to that comprise a comprehensive proof of this. Okay, this is here is just a skeletal proof of the Bolzano-Weierstrass theorem. Okay, so before we go, let's have the last theorem under sequence of real number. And this sequence is this theorem is known as the theorem of nested interval. So let's quickly state that. Okay. So because what we have experienced here is that the interval theory is in form of a nested interval. Okay. So here, see that let an and bn be two sequences such that the two sequences such that if you take this, the sequence here, okay, if you take this as the first one of this interval, and you take this as the second one of this interval, what we observe is that this, okay, the superset of this, okay, and this also is superset of the next time. So, to the extent that we now have the interval A to B2, and this is the interval E1, B1. Okay, so what is happening is that this A and B are two sequences, two different sequences. Okay, but both of them satisfy the nested form as gravity. Okay, so what this theorem is now saying is that if this happens, then the infinite intersection of this interval, the infinite intersection of this interval is never ending. Okay, and moreover, okay, it means non-empty means there is a single element in the nested interval. Okay, so that would be a single element. So what you are saying in this sense is this: if you have two intervals, if you have noted this, I just want to quickly try what is happening here. If you have an interval, let's do that on the plane. Let's say from here to here, this is A1, this is A2, this is B2, so this is B1. Okay. Let us also say this is B1 and this is A1. Okay. So if we rule out this on the plane, we have it from the circle. Okay. This A1 B1 is this interval we have here. Okay. We are just doing this on the plane in order to give a kind of a planned view of what we have done here. Okay, we can easily do that on a single line as well. Okay, so now what we have is that the entire interval a to b2 is contained in a1 b1. The meaning is that this a2 is somewhere around here, this b2 is somewhere around here. Okay, a2 here, sorry, b2 here, a2 here. So this can be of this form. Okay, that's the meaning of this. Okay, being a sorry, this should be, let's write this. This should be a1 b1, a2 b2, and this goes to n minus 1, and this is n. Okay, this part shall be sent over there. So the next interval after this is a3 b3. Okay, and that also contains there. So if you continue this, okay, up to the last element, okay, we'll see that the last ascending to infinity, okay, this will go, this a and b, okay, to meet a number L. Okay, let's say the limit here is L, that is the limit point. Okay, the limit L. Okay, this AN is going to this point, this BN is also going, okay, so each of them go independently. Okay, and I just say this is just an L. Okay, an L. What I'm saying is that if you take the intersection of all these nested interval, okay, what will get is just a point, and that point is just L. Okay, and that's what the theorem of nested interval are doing. So one of the application of this is in the study of numerical analysis, where we use one of these numerical method called bisection method. Okay, bisection method. One can use that to implement the theory that we have here. Okay, you recall that bisection method is one of the approach we use to find the roots of a nonlinear function. Okay, so that's one of the approaches. So here is a simple explanation of the theorem of nested interval. Okay, so after this class, I'll give you a comprehensive notes where you can go through some of these theory and their proof. Okay, so but for now, if you have any question, okay, you can let me know, or you can submit your question in the group. Okay, so can I take the attendance now? I think it's more than to stop here, so we can take attendance of those who have participated. So that's all for the class. So let us meet in the group for further discussion.